Welcome everyone. So today's chapter we'll be looking at elasticity. Now this is a very small chapter. Um, to be honest, it's not going to be very long, this one. And we have covered some things as well in the previous chapters. I'll just tell you where they're coming from. So if you're enjoying our videos, you've watched our videos, you're enjoying our lectures, please guys support the channel by subscribing, liking a video. Also, you can just share it and also just get your friends to watch the videos, different universities, because mostly the content is focused on university students. But if you are in metric high school, for instance, you could actually check out the chapters. They are also suitable, as most part of it are suitable for high school as well. And there are worked examples as well, so that is helpful. Otherwise, guys, so elasticity basically is basically how materials respond to deformation. That's basically how what you could actually describe as elasticity. So you have seen this, for instance, when we're doing energy and power, work energy and power, we describe the spring. So let me say you have a spring like this. And then what you do is what happens when you apply a force and you actually stretch the spring. Okay, so then there's the force that you'll be applying. Now you remember that we said this applied force is basically just given by k delta x. What is delta x? So you say this distance is x0, and then this will be x0, and then this is going to be x1, x0. So the change in delta x basically is just this distance here. All right, so you know everything about that. So basically it's a stretch. You could say this change in x is x as well. It's fine, doesn't matter. Okay, then we said if you're stretching the spring exerts a force in this direction. All right, and then the force that the spring is the restoring force. That's the force that the spring actually exerts, and they said that that force is actually given by Fs, which is going to be equals to minus y because it's opposite the applied force, but the magnitude of that spring is just delta x like this. All right, so we said that this is the spring force that you can have. I mean, we can actually do examples because we did not do examples when we were doing energy, but you could also check out that lecture. All right, so let's just look at a case whereby you have a horizontal stretch and then you have a vertical stretch as well. All right, so a horizontal stretch, for instance, let me just say you have a spring, there's a spring, and then you actually apply force. I don't want to stretch it like that, it makes it straight. I don't want that. Okay, so you have a spring. All right, then you stretch it. It's already stretched because you have applied a force. All right, let's just say our delta x is going to be 3 centimeters. Then we want you to actually find out, and then we say that we have applied a force of 70 Newton, and then we just want you to find the spring constant for the spring. So we could do that. We could say, well, Fs now, since you want the spring constant, sorry, since you just want the spring constant, it's fine. We know that in principle it's going to be like that, but you can just ignore the negative. The negative just tells you that the spring is going to restore. So you could just say Fs is just going to be, you just take the magnitude, just focus on the magnitude of Fs. All right, so this is the vector and then this is the magnitude, of course. All right, so you could put a vector here. Okay, if you just look at the magnitude, it's fine. Then you say, well, k is just going to be Fs over delta x, and then that is going to be equals to 70 divided by 3. All right, so that's going to be equals to 23 point something. Okay, 23.3. And then the units is newtons per meter. All right, that's basically the spring constant. All right, so another common way in which sometimes these questions will be phrased, you can have this in a different number of ways. Let me say, for instance, you have a spring, there's a spring. This is how long it is initially, and then what you do is you put a mass. There's your mass, and then the spring actually is compressed, and then let's just say the mass that you put here is 7 kg. All right, and then you are told that the spring constant, you put a 7 kg mass, and then you are told that the spring constant for this one, let's just say it is a 35 Newton per meter spring. So the question is, what would be your delta y? Of course, like a change in y, okay, which is a stretch. What would be your stretch, or your compression in this case? So again, you could say just look at the magnitude. Don't focus much on the the direction. Of course, when you substitute here, you could substitute. I mean, you could say this is y0, which is 0. Then this is going to be y1, which is going to be minus something, right? So you do expect to get your stretch to be negative. All right. So let's just look at the magnitude of delta y. So the magnitude of delta y is just fs over k. And what is Fs? So since this is the mass, you would say that, okay, fine, there's a force of gravity mg that is pushing this mass. So this spring is actually experiencing a force due to this weight here. So the force is going to be mg, and then this is going to be k, which is going to be 7 multiplied by 9.8, and then you're dividing it by 35. And you'll find that, well, this spring is going to stretch, the magnitude is going to 1.96 meters. So, I mean, delta x as a vector is going to be minus 1.96. Why? Because it's going to go down meters. All right. So that's what you can actually find. That's how you can actually find the stretch of that. All right. So it turns out when you actually apply forces, there's generally three types of forces that you can apply. You could apply sort of like a tension force, which is like a force that just works on that area perpendicular to the area. So you could apply a force like this. This is the area. Then you're applying a force in this direction. This is going to be a tension force. This is your area here. So it's perpendicular to the area, as you can see. You could apply a force that is parallel to the area. There's the area, there's the force. Now this is known as the shear force. You could also apply a force in all directions. So your force is being applied in all directions like this. So this is more like your volume. You're applying pressure on the volume. All right. So this one will be your area here. So this one is parallel to the area. And then this is what we call a shear force. So it turns out that in all these situations, what you're doing when you apply this force, you deform materials. Now, we know examples of this. If you take rubber, you take plastic, you pull it, it gets deformed. Plastic doesn't come back, a spring comes back, it gets deformed, and then it comes when you leave it, and then it comes back. So we can actually explain this in sort of a graph, right? So what I could do in a graph is I could look at what happens as I actually change the length, right? So which means that I have maybe something like this. There it is. It's a rod like this. There's my rod. And then I apply a force, a tangential force, it gets stretched. So what happens as I keep increasing my force? That's basically. So as I keep increasing my force, this actually becomes, this was the length LO, the length from here to here. So you can see that now the final length is just the length L. Maybe you don't see, let me just make sure it comes back to the screen. And then this is the length L. Okay, so I could find this length here is actually going to be changing L, which is going to be L minus LO, basically. So I could actually evaluate what happens to this as I'm changing the length. So it turns out, generally, when you change the length, it stretches linearly, so meaning that it follows a straight line. Okay, there's a straight line. Okay, so it follows a straight line. So when it's following a straight line, it is obeying this law that is called Hooke's law, which is the law that we found for the spring, which is Kx, which is your force basically changes linearly with your change in displacement. This is known as Hooke's law. All right, I spoke about this when I was doing energy. So as you continue stretching it does continue increasing, but it's no longer linear, right? But if you were to leave the object, it will go back to its original length, which is going to go back to 0. So here, for instance, in this region, this is known as the elastic region. I'm going to label everything, which means that when you stop applying the force, it goes back to where it was. So more like the spring, there's your spring, okay? When you apply a force, it stretches. When you leave it, it comes back to where it was. So we still say it's elastic. Okay, so as you keep increasing the force, it then gets into a situation whereby it is no longer linear, but it actually is still increasing, the length is still increasing, the force is still increasing, so you are actually still stretching the material. But here, if you were to leave it, it won't come back. So this is more like a plastic, right? Whereby you pull a plastic, it doesn't come back to what it was before. All right. So here, this is your force. So now if we label it, when you actually reach some point here, all right. Now this point here, this is where we call the proportional limit, meaning that it's going to be proportional, it's going to obey Hooke's law until at this point. So there's a particular length that once you pass that length, it will no longer obey Hooke's law. Now, in all of this, for instance, from here, while you are still stretching it, it is still elastic, meaning that when you leave it, it will come back to the original position. Okay, so you still have the elastic region. Okay, so this is the proportional limit. Then this one here, this is the elastic limit, meaning that this is it can be elastic up until this point. Now, once you start coming in here, this black region here, this one here, I thought I chose a different color. This region here, it is now plastic, meaning that if you leave, you stop applying force there, it no longer comes back to its original position. It stays deformed. So this is the plastic region. All right. So these are just properties that materials have. All right. Then there's a particular point that you reach, which is this point. When it reaches this point, if you continue pulling up until that point, basically you experience rupture, meaning that basically you just have a situation where the material breaks, so you can basically tear it into pieces at that point. All right, so this is how elasticity, this is how it affects materials. This is what happens as you apply force on materials. They are just going to expand, not expand, they're just going to elongate in this sense. How they are going to do that is different, and then I'm going to discuss it now. All right, okay, so there is we can actually for a region where it actually obeys Hooke's law, whereby it's linear like this, we can actually find out the stretch. Okay, so there's something called Young's modulus. So if I have a material and I apply a tension force on that material, this is the area, which means that the force is perpendicular to the area. I'm applying the force on this area. Somehow just think of like I'm applying the force on all of this area. And then this is the length L0. So when I apply a force, let's just say force F, not tension, force, of course that force is tension. When I apply a force, this material becomes longer. It's a rod, it's a rod, you can think of it like a rod. It becomes longer, so it ends up with a length L. So you can see that from here to here, this becomes changing L. Now changing L is just given by the final length minus the initial length. Okay, so it turns out we can find a constant which tells us how strong a material or how hard is it going to be to deform that material. So if I apply a tension force, so if you apply, and then this depends on the shapes, because you'll see it depends on the area, and different shapes have different areas. So it's given by the force that I'll apply over that area. It's going to be the Young's modulus, which is this y, change in L over L0, which is the original length. Okay, now this constant, this variable here changing is known as stress. This force over area is known as stress, right? And it is measured in Newton per meter squared, which is the same as pascals, right? Okay, this is also actually known as pressure as well. This force over area is actually known as pressure. So you can think of stress as pressure, basically. Now this one here, change in L over L0, this is known as strain, so I'm going to use this. So this is the strain. All right, so this is the strain. Now this one doesn't have unit because this is meters divided by meters, and then they cancel on it. Doesn't have any unit, this strain. Okay, so the Young's modulus Y is therefore can be given by stress, okay, divided by strain. Why? Because this is stress is equals to Young's modulus strain, if you actually simplify this equation. So these equations are very important. This equation here is very important, and this equation here is very important. So now let us just define that there's a graph, there's a special graph for stress and strain, and then maybe we'll just look at one simple example. All right, so you could actually plot a graph whereby you have stress this side. What happens is you apply stress, and then the strain this side. All right, so it is known as the stress and strain. So it follows more or less what I've described before, whereby it's going to be linear, 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 linear. Then what happens is stops being linear. It stops being linear. Then afterwards, it continues to increase, but it becomes non-linear. It just follows whatever. All right. So this point here, this is known as the breaking point or rupture. All right. And then this is still the elastic region. And then this is still the plastic region. So nothing has changed, meaning that as you continue applying stress, there's a point whereby it's just going to be permanently deformed. Okay, it doesn't break, but it's going to be permanently deformed. And then at some point, a particular point, which is this point here, it's basically going to break. All right, it's going to break at that point. Okay, all right. So at this point here, the strength that you get here, this is known as the yield strength. And then here, this is known as the ultimate. This is the ultimate, I think it's I here, strength. Okay, so this is how basically you can so this is the yield strength is basically when it's still the maximum strength where that you can apply on the material and it's still elastic, and then the ultimate strength is the maximum strength that you can apply on the material before it breaks. So you can think of it like that. All right, so let's just look at an example like an AG. All right, so let me just say I have an iron rod. Okay, so this is just an iron rod. There's my iron rod. All right, so you are told that the radius here r is going to be 5 centimeters. So change this immediately to 5 times 10 to the power minus 2 centimeters immediately. And then you are going to stretch it. Then you are told that the stretch, which is change in L, is just 2%. It stretches by 2%. So what that means is that the change in stress is going to be 0.02, which is what 2% is. Remember, 2% is just this, which is 0.02. Okay, so it's 0.02 of the original length, which is LO. So you're not given LO. All right. And then you are told that this is ion. So basically, you know that the Young's modulus, you can look these values in any textbooks or in the internet. The Young's modulus for ion is going to be 100 times 10 to the power 9. This is pascals or Newton per meter. It's basically up to you. All right. And then you are actually asked to find the force. So what you're going to say is the force over the area is the Young's modulus, that over L0. So which means that the force is going to be equals to the Young's modulus, changing that L over L0 multiplied by area. So what is that? This is going to be the Young's modulus 0.02 LO over LO, because this is a change in L. Okay, then you multiply by the area. If you look at the area, this is a circle. So I've already taught you when I taught you circular motion that the area of a circle is pi r squared. So this is going to be pi r squared. So you're going to multiply by pi r squared. Then when you do this, everything here, you can now substitute. It means that the force is going to be the Young's modulus, 100 times 10 to the power 9. And then this is going to be multiplied by 0.02, because this is going to cancel with this. Then you're going to multiply it by pi, and then you multiply it by 5 times 10 to the power minus 2 squared. Then it turns out the force that you must apply just to stretch this material by 2% of its original length is, okay, so that is going to be 15.7 times 10 to the power 6 Newton. Okay, so that's a lot of force that you have to apply just to change it by 2%. Okay, so that is the one if I'm applying the tangential, if I'm applying the tension force. So what happens if I apply the shear force? Okay, so what is this shear force? So the shear force basically is, just think of, I have a cube like this. There's my cube. All right, so I'll call this the height here. I'll call it LO. This is what I'll call LO. Then you basically apply a force here. So the force is applied on this total area. So just think of it like you have something that is covering this whole area, and then you're applying a force on that. So the force is parallel to the area. So normally you'll also need another force here that is going to counter it. So something like friction, or it's basically clamped or something like that, that is going to oppose that force. And then what happens is you deform the material like this. It's more like a jelly, you know, if you look at jelly when you cook it, and then you can deform it like this if you push it, and then it just deforms like that. So I think that's one of the good examples that you can actually see. Okay, no, I want it to be like that. Okay, so you can see that it's deformed. So this is still the length, but now it's away from the length. So this is still LO. So if I draw a line here, so you can see the line from here to here, I'll call this delta x. So it is now deformed by some angle theta here. And sometimes you may be required to actually find out what this angle theta is going to be. All right. So in this case, for instance, you're still applying the force here. There's the force. And then in that case, and then there it is. Okay. So you're still applying the force. So here, the force over the area, this is the area that you're applying the force, is given by, so this is the shear force. So the shear force will be given by the shear modulus. Remember you had the Young modulus when it was tension. Now this is the shear modulus. Change in x over LO. So you do need to find change in x in this case. Okay. So for instance, if I say to you, I'm going to apply a force, maybe let me just say I'm going to apply 200 times 10 to the power 4 newtons force, and this is aluminium. All right, so the aluminium has a shear modulus of 25 times 10 to the power. Again, you just use any textbook, you can get these values. Normally you'll be given these values or all these values as well when you're writing a test. Sometimes it depends on who's lecturing you and what did they prefer. And then the initial length, let's just say it has an initial length of 20 centimeters. So it's still the same thing. So I'm just giving everything values. Okay, so what I want you to find is I want you to find the lateral displacement, which is change in x. I also want you to find theta, which is this angle here. All right. All right. So in order for you to find that, you'll need the force, you'll need the area. So the force is parallel. So you'll need dimensions because you need to find out what this area is going to be. So what I'm going to do is I'm going to say this is going to be my width, and I'm going to say this is going to be 13. This is equals to, and then this is going to be 13 centimeters. Then let's just make this 20 centimeters, same as the length. So I'll call it the length, and then I'll just make it 20 centimeters. All right, and then let's try and find what that will be. All right, so the area is, let's start with the area. The area is just going to be this section, the length times the width. So it's going to be this section. So you remember you had the length here. And then I said this is I'm going to call this, I'm calling this the width. All right, so all right. Now if I do it like that, this is the area, this is where I applied my force, and this parallel to that. So I need to find this area here, which is going to be this length times that width. So you could change this, you should change this. So basically my length is going to be 20 centimeters. You should change this, and then my width is going to be 13. So you should change this into meters. And then after changing into meters, try and work in SI units. You must always work in SI units. try and change this into meters, and then after changing into meters, and then you find that one. So if you change it into meters, the length is 0,2. You multiply that with 0,13, and then you just find out what that area is going to be. Right, so the area is going to be 0,026. All right, that's going to be the area. It is now meter squared. All right, so I'm going to use this formula now. So I have this one, I have this one, I have this one now I have this one. I can just find what delta x is going to be. So my delta x is going to be equals to, I have to cross multiply, take this, multiply it with this one. So it's F multiplied by LO divided by area is below. So I want to make this a substitutable formula. So I have to divide by that. All right, and then there it is. Okay. Then I can just substitute everything that I have here, which is 200 times 10 to the power 4. And then this one, change it into meters as well, is 0,2. You just divide centimeters by 100 to get it into meters. I taught you this chapter. And then afterwards, you take the area, which is 0,026. And then afterwards, you use the shear modulus, which is 25 times 10 to the power 9. All right, so this Pascal's basically is pressure. Then you'll find what change in x is going to be. So my change in x is going to be equals to, so it's 6.15. Let's just leave it in 2 decimal places, times 10 to the power minus 4. So roughly, I mean, if you were to change this into millimeters, you're looking at like something like 0,15 or 0,2 millimeters basically. That's what you're looking at. So that's very small when you're looking at it. All right, so now when you want theta, let's look at it. So I have this distance, it looks like that, remember, and then we said this is going to be L0. So we know this one. Then we said this distance is going to be delta x. Remember how it looks like? It looks like that. All right, I'm not going to draw the whole thing. And then we said theta is going to be here. So I have delta x, I have that, so I can use tan. So I could say that tan of theta is going to be equals to the opposite, which is delta x, divided by L0, not L. So it should be L0 even though they are equal. Then you just substitute that. So you basically use it as this, times 10 to the power minus 4. And then change this into meters as well. And then you can get your theta. Basically, you just say the arctan, right? So you just say shift and then 10 on your calculator. Okay, so basically it is 0,2 degrees, right? Roughly is 0,2 degrees. Okay. All right, so basically this is how you can actually find whatever it is that you're asking you to find. Whether they want you to find the angle theta, they want you to find the lateral displacement or the deformation, or the distance at which it will be deformed, right, from the original position. So it could be asked in different ways. Okay, so I think this is it, and then we can actually now move to the next one. Okay, so the last one is going to be the volume change. All right, so the volume change is, just think of, you have a sphere, a spherical object. This is a spherical object. There it is, a spherical object. Okay, and then you start applying pressure on this sphere. What happens when you start applying pressure on this sphere, which is just force per unit area in a way? All right, so but then you're applying it on the whole, you're applying it on the whole volume. So every side is feeling pressure. The front, the back, the sides, below, above, everything is feeling pressure. So you end up with your object being deformed. So this becomes the initial volume. So the initial volume was this one. It was this big initially. So this is the initial volume. Then the final volume is this one. So you can actually find the change in volume, which is V minus V0. So you can actually say pressure. All right, some textbook will say change in pressure. It depends, because normally when it's like this, you have an atmospheric pressure, but we'll get into that chapter. So for now, let's just say pressure. Let's not use the change in pressure. Is going to be, you could use a negative, and then depending on how you're changing your volume, because I'm deriving this using the pressure that is decreasing the volume. So basically you could say that you could put a negative or not, but it's fine. Let's not put a negative. This is the bulk modulus, and then this is delta V, and then you divide it by V0. Okay, so this is this. So very few now, normally when you go to textbooks, you just find that the bulk modulus is just listed for very few materials. Now, you normally find that in most of the test scenarios, they like asking you the bulk modulus because you don't know it. So they'll give you scenarios and then they'll just basically get you to estimate it. All right. So that's generally what you would actually experience normally with these ones. All right. So for instance, I mean, it's a very simple example of this one is if you have a material like brass. So what you're saying is, okay, fine, if I'm going to apply pressure on this material and it decreases, so it's going to decrease by 3.8%. I want it to decrease by 3.8%, and this is brass. All right, so I'm applying pressure, it decreases by 3.8%. So brass has a bulk modulus of 80 times 10 to the power 9 pascals. All right, so that's basically the bulk modulus of brass. All right, so if that is the case, they want me to find the pressure, so this is just that. So if it's going to decrease, right, so the change in V is going to be negative because it's going to decrease, so it's going to be negative. All right, so in that way, I'll have to, if I expand, I have to apply pressure maybe going outwards. So if it's negative, it's going to be going inwards. So I'm expecting that I will have to apply pressure inwards in order for it to decrease. Okay, so it's going to be negative. They say by 3.8%. All right, so 3.8%, you divide that by 100, it becomes 0.038. Then the original volume, right, which is the original volume. Okay, so if you just wanted the magnitude of pressure, you just don't have to put this minus, but if you just does not put the minus, is fine. And then the minus just tells us that it's going to cause a decrease. That's why I just put a minus there to say it's going to cause a decrease, but it is fine. Let's just calculate the magnitude of pressure, then you don't have to put the minus. All right, but then if you just wanted to know what direction would that pressure be, and then you say it's in the minus, and then you say this is when it's going inwards, and then it's going to decrease the volume. It's going outward, it's going to increase the volume. All right. So in this case, what you're going to have is you're going to have a situation whereby this is 80 times 10 to the power 9 multiplied by 0.038. Remember, these are going to cancel. So what is that? So the pressure that will be experienced will be 80 10 to the power 9, and then you multiply that 0.038, and this is going to be 3.04 times 10 to the power 9 pascals. So that's how much pressure you must actually apply on brass, and just in order for you to decrease it by 3.8%. All right, so the last one that we talked about, you remember I said that it's possible for you to apply force such that you can actually break the material. So that is basically fracture. So there is something called fracture. So this is the situation whereby if I have a rod, there's my rod. If I apply a force, if my force is very strong enough, I can actually fracture it. And then I have the second piece here. So I can fracture it. So there's a force that I can apply such that this material basically fractures. So generally, you have to apply force in both directions, and then it will fracture. You could also compress it, for instance, right? You could compress it. Let's use the same rod, and then you could compress it. So you apply a force in both sides going that way. So it will then compress it. Now, when it compresses it, it becomes something like that. So this is the point where I say you now fractured it. All right. So again, some textbooks don't list this, some textbooks do list this. One day I think I'll make a video as to what textbooks that are very good that I think you should use for what type of physics, because they're not the same, the levels are not the same. So maybe I should one day I'll just make a nice video so that I just to guide you guys as to nice textbooks that you actually use, that I generally use when I'm teaching, that I recommend that students should have to actually learn good physics. All right, so I'll just see if I can do that. All right, so this is fracture. Normally you get something that is called tensile strength. They will release them like tensile strength. Sometimes they say compressive strength, compressive strength, and what else would you get? Let's just consider these two. All right. So these are the strengths. So they'll be different for different materials. The most important thing here is that these strengths are given in Newton per meter squared, which means that they are given in pascals, which means that these actually are equals to whatever the strength. If I call that strength X, whether it's tensile or compressive, if I call it that, it's just given by force divided by area. Right. So I mean, a good example would be if I have like a guitar string which is made of iron. I believe it's iron. So if you have a guitar string, for instance, what tension must be applied, and then it depends also on how the radius of the string. If you have that guitar string, and then what tension must be applied to break it, and then of course you will just say that tension will come from here. If you know the radius, this is going to be the area, and then you find that from the textbook what tensile strength, and then you can basically find it. So I'm not going to do an example on this one. It's just that I felt it's going to be important to mention something along these lines. All right. Otherwise, guys, I think this is fine for this chapter. As I said, it's a very short chapter. It's not a very long chapter. So I normally prefer to just teach it separately as a chapter. So yeah, I think this is it, guys. So again, don't forget to support our videos, and then otherwise, see you guys whenever I upload the next video. Cheers.